Alright, so yesterday we finished up with the absolute versus conditional convergence after the alternating series test. So that was kind of telling us what? Do you remember what that was telling us? The absolute versus conditional convergence. How did that work? How did we find that, or how did we determine that?
The sum of the absolute value of your function is the same, but if they both converge, then it's absolute convergence. If some your function converges, but your absolute value of it diverges, then it's conditional.
Exactly. So what we're saying with the alternating series is we have these plus and minuses, so we're constantly adding terms and subtracting terms. So if we have the series like that that converges, and then we take the absolute value, so the absolute value changes all of those minuses to pluses. If we can add all of those terms and it still converges, then it's absolutely convergent. But if we take the absolute value and change all those minuses to pluses and it diverges, that's when it's conditionally convergent. Very good. Alright, so now we're going to go to the alternating series. So we're going to suppose that we have this alternating series that satisfies the conditions. So the limit is equal to 0, the an is not increasing, and then we're going to deal with this right here, the Rn. So that's the remainder, or the error bound. It can be said as both, the error or the remainder or the error bound. Now, we have the absolute value of Rn there, and that's less than or equal to this an plus 1. We can also write that as Rn is equal to the absolute value of an plus 1. So once we get into an example, that'll make a little more sense what we're talking about, but you can write it in this way. So we're going to find this error bound, and the error bound is going to be no greater than this term that we picked, this an plus 1. So we're going to find the summation to some point, which would be this Sn here, and we're going to subtract off and add that Rn, or that error bound, and that'll find our the bounds within our error, or our summation would be. So our summation would be within these bounds here. So it's similar to the one we had done before, but I think once you do an example with this one, I think this one's pretty easy. So if we take a look at number 18, these questions are going to be asked two different ways. So each one, we're kind of doing the same thing, but it's asked in a different way. So we'll focus on 18 first. Approximate the sum of that series there by using its first 6 terms and find the error. Use your results to find an interval in which S must lie. So they're talking about the first 6 terms, so we need to find the sum, and there's not a lot of room here. We could maybe write it down here and then just label that it's for 18. We need to find the sum of 6. Well, you have a calculator. So you need to go to math and 0, that's where the summation comes up. And we're going to the 6th term. Divided by bx factorial. So that's in math, and then you go to probability in 4. Anybody having trouble getting to this point? Need help typing in the calculator? We all getting the same answer? Okay, so the sum of 6 terms is 0.63194. That's where I'm going to stop. So this term here that we found is our AN term, okay? So in other words, you could think of that as your AN term. What would be your AN plus 1 term? If your AN was the sum of 6, what would your AN plus 1 term be?
Sum of 7.
Okay, we're talking about the 7th term. The AN plus 1 would be your 7th term. So what we're actually going to do here to find that error is you need to find the error of 6, because we're talking about the summation of 6, is equal to, we just took the Rn from up here, so R6 equals the absolute value of what? What are we actually taking the absolute value of? Okay, so how would we fill in our 7th term? If we're calculating the absolute value of the 7th term, we're just going to plug it directly into here. So we're going to have -1 on the top. When you take the absolute value, does it matter what exponent you have on -1? No, you're just going to have a 1. And on the bottom end, well, now that's 7 factorial. So you're finding the value of that 7th term. This isn't the summation of 7 terms. This is just the value of that 7th term. And you can go ahead and calculate the value of that 7th term. So what is our value of that term? The value is what? What are we going to write down? Anybody? I have the value on my calculator. What is it? Or how do I write that? Yeah, this E is like the times 10 to the -4th, so we get 0.000198. Okay. So we know our sum of 6 terms is this. We know the value of our 7th term is this. So how are we actually going to find our error bounds? Our summation is going to be within what bounds?
Why do you have R sub 6? What is that?
This is coming from up here. We're talking about, this is meaning the remainder or the error if you have a sum of 6. So we're finding the error for the sum of 6. But when you find the error for the sum of 6, you need to use your n plus 1 term. So in this case, we're using the 7th term because we're doing the sum of 6. Okay. So we're going to be able to find the bounds within our convergence for the sum of 6. But if you add another term, just like we did with the test before the other convergence test, if you add another term, that's going to get smaller and smaller.
So we just found a term of 7.
Yes, this specific term right here is this value. But we found the sum of 6 terms. That's because our error is going to be within this value. Okay? So now what do we do with this value in our sum? Okay, so we have 0.63194 minus 0.000198. So you get 0.6317. So that's your lower bound. Now remember, this was for an alternating series. We're doing subtracting and adding because at the sixth term, this is what your summation is. But remember, we're alternating, so you could be less or you could be a little bit more. So that's why we're subtracting and adding for the error bound. So we have this as our lower bound. And for the upper bound, we take the 0.63194 and add the value of the seventh term to it. So again, we don't know exactly what it converges to, but we know by this alternate series remainder at the top that if we take the summation to the 6, find our seventh term, we can calculate our bounds. So our convergence is within these two bounds. So pretty close already, 0.6317 and 0.6321. And that's all that's asking for that problem. You found the bounds of error. Are we okay with that process we went through there then? You're okay, Eric, with that 6 in the seventh term?
I think so. This is
Okay.
only for alternate series.
Correct. This is just for the alternating series. So if you look back at the top, the alternate series remainder. So the remainder, or the error that we're talking about, well, we found the alternating series up to 6. You take your an plus 1 term, so one more term. That's going to tell you the value for your error bounds, what you're going to subtract and add.
And the reason we use the next term is because it's flip-flopping back and forth.
Yeah, it's going back and forth between adding and subtracting. So we know this is the next term, but we don't know whether it's going to be a little bit less or a little bit more because we keep alternating back and forth. Okay? And as we go to the next term, say the an plus 2 term, you keep getting smaller and smaller if you're converging. So if you go to the 8th term, well, it's going to be smaller than this value.
So could we find a more accurate error?
You could. If you go further and further, yes, you would find a more accurate value, correct?
So why is the formula just the next one? Would it ever ask us to find like
You
there
could.
with R like 12?
You could. The next one is kind of builds upon that idea that you're mentioning. When we go to the next one, I can kind of explain that. But yeah, the further you go, the more narrow that's going to get. Just like with the integral test when we did the convergence there for the error bound. All right, so that's for 18. Are we okay with that? I'm going to erase that to do 19 if you're all okay. Copy that. Okay. All right, so 19 is worded a little different, and they're asking something a little bit different. We're not actually asking for this part here. We're just asking for an approximate sum of this infinite series here that has an error less than 0.001. So we know in the previous problem we found a sum, and we found the error, and we subtracted and added that to find our error bounds. So in this one we're not actually finding that error bound, but we kind of need to guess and check almost in this problem to figure out which term is going to get us less than this value. So again, once we find this term, once we start through the process, you'll see what I mean by finding a term that's less than this. But again, going back to Eric's idea, well, why can't we just choose a bigger term or go bigger because it'll be smaller and smaller as we go? Well, you could. You could start big and say, well, we're going to check the summation up to 50. Well, you find that it's some really, really tiny number. Well, that's obviously going to be smaller than this. Well, yeah, you can use it and say the approximate sum is this. But you'll see that as we start the problem. So if we start plugging in just 1, you can use your calculator if you want, but for the first one, we plug in 1. What are we going to get as a value?
Could you approximate the sum of it to like number like 5 or whatever, but then have your error and then use like the 10th term for it or whatever? Or does it always have to be the one after that? Because if you use the 10th term for error, wouldn't you still get the margin error? Because as it flip flops back and forth, it's going to be smaller.
Well,
It goes toward a number.
you have to use the next term, because if you go to the AN, if say you went up to the 10th term and you were only using 5, well, that 10th term is a lot smaller than that, let's say, 5th term you were using. So when you add and subtract that error, your value may actually be outside those bounds. Because as you take the sum, if you would take the sum up to 9 and you want to use that 10, your number could vary and be down a little further or up a little further at that point. So when you take that r to the 10th, or your an plus 1 would be 10 at that point, when you subtract that smaller value, well, you're closer because you've added values up to that point. So if you are at r5 and you use 10, you still may be without your actual convergence. It could be outside of those bounds.
So it wouldn't be as accurate because you're using the large number still.
Correct. You need to use the value right after it, but you could use r sub 9 and then use the 10th value.
Okay.
But you can't use a value that's further away from it. Okay? It's a good question. All right, so on the next one, if we plug in 1 for this, what would we actually get for a value?
1.
You get 1. Okay? Then if you plug in 2, well, we're going to get negative because of the top, and 2 to the 4th. So we're going to get 1 over 2 to the 4th. The next term we would get plus 1 over 3 to the 4th. So we're just writing out a little bit of this series right now. Then we'd get a minus again, 1 over 4 to the 4th. Plus 1 over 5 to the 4th. So what we're looking here for is, and we may have to go a little further, we're looking for one of these values to be less than this value right here. We want an error less than 0.001. On that previous problem, we had found with that 7th term, the error on that one was the 0.000198. So we went to that individual term 7 on that problem, and that was the error. So we need to figure out which term here in this series will get us to less than 0.001. Now again, kind of going back to what Eric said, once we find that term, the first term that's less than 0.001, every term after that will also be less than that error. Okay? So the first one obviously is 1. But what is the value of 1 over 2 to the 4th? We're going to find each of these values. So 1 over 2 to the 4th is what? Point what, sorry?
1 over 16.
We want the decimal versions because we're trying to compare it to this.
0.063.
Okay, 0.063. Let's go to the next one. 1 over 3 to the 4th. Okay, so we got a little bit smaller. Let's keep going. Okay, so we're still getting smaller. Are we smaller than the 0.001 yet? Not yet. Let's go to the next term. So either 0.002 or 0.0016. Are we less than this yet? We're really close though, huh? So we need to go one more term and check it. So minus 1 over 6 to the 4th. And hopefully this one has an error less than 0.001. What did you get, Abby?
0.0007.
Yes. So we know this term here is less than 0.001. So what we're going to call the error is equal to the absolute value of your first unused term. The error is equal to the absolute value of your first unused term. So if you think back to what I just said in the first problem there, we took the sum of 6. Your first unused term was term 7. So we took the absolute value of that unused term. So we want our error to be less than 0.001. So what's our first term that's less than 0.001? Well, in this case, in this problem, it's our 6th one. So this one here is what's known as our first unused term. This is the error that we're going to be dealing with, and this error is less than 0.001. So all they're asking us to do in this problem now is approximate the sum, but the sum to what value? What value do you think we're going to take the summation to? Summation to 5. So again, you can use your calculator for that and type that in. Go to math. 0 is your summation. Okay, so the summation is 0.94754 up to the 5th term. So we know that our error in this answer is less than 0.001 because our next term is 0.007. And each term after that's just going to keep getting smaller and smaller and smaller. So we know the error here has to be less than 0.001. So we know it's going to be 0.49 something. Okay? So that's the reason that we're doing this. You're finding an error, and we know that this has to be within 0.001. So it's getting close. Now again, back to what Eric said earlier about, well, can't we go further? Well, yeah, we know this term is less than 0.001. Each term you keep on going is going to be smaller and smaller and smaller. So the further you go, the closer this will be. And yes, any term bigger than the summation of 5, the error would be within 0.001. So once you find that first term, any summation past that will also be within that error bound. Okay? Do we have any questions about that? So it's 2 different ways those questions can be asked. They could be asking for the error bounds, the lower and upper bound, or they could be asking you to find a summation that has some error less than a certain amount. In this case, the 0.001. We're okay with that idea? Okay. Well, that's all we're going to do for today.